Hi, I hope you're here to hear some really cool stuff about the work I've been doing for the last few months. It'll make me feel much better about the long hours I've put in. My name is David Byte, Senior Technology Strategist with SUSE.
And I'm Carl Wiedemeyer. I'm a cloud solutions architect with Intel in our sales and marketing group. And I focus on software-defined storage, predominantly Ceph. So I've been helping Dave the last couple of months.
Thank goodness.
I'm
All right, so we took care of that. So the agenda, we're going to kind of cover the project goal that we embarked on, gosh, what was that, like 9 months ago?
Was it that long? Yeah.
For the first discussions, yeah. The
a
actual work only started like 4 months ago, but we'll say 9 months. We'll talk about the hardware environment, the testing methodology and tools, some interesting results, and I will say there are a lot of numbers in my presentation, so I hope this proves interesting and helpful. Some final recommendations coming out of this, and just a little information about what I still have left to do, because this is not yet complete. There's always more to do, right? So first, we're going to make the Intel attorneys happy. This is their legal disclaimer. Please read it. So we'll finish this up in 20 minutes.
Yeah.
Blah, blah, blah. It says, your mileage may vary.
We have to.
Yeah. All right, Carl.
All right. So, just first off, why are we working with Dave? Why help SUSE? I just wanted to. A lot of times, Intel, most people, they don't even know necessarily how much of a software organization, how large it is, and how much of a contribution we do make into the Linux kernel and Ceph in particular. Linux kernel, we're consistently in the top 10 contributors, company-wise. In fact, this year we were #1 contributor to Linux kernel. And Ceph, we're a major contributor. And as you can see, we've been involved with Ceph since back in 2014. Obviously, primarily, we've been working things that optimize for Ceph on flash. So you can see where we started work on BlueStore optimizations, BlueStore SPDK. You guys might know what SPDK is. It's essentially DPDK for NVMe. So it's a lockless polling driver for NVMe, for the NVMe driver, to remove interrupts and things out of the system. And then, of course, erasure coding. So we've done a lot of work with Red Hat and SUSE on optimizing erasure coding. So you're starting to see more. In fact, I think this is the last release. You can use erasure coding with block storage. Not sure why you would, but at least you can now do it. And this is more important, though. Luminous and into 2019, the things we're working on in particular, in optimizing this DPDK SPDK stack and that's really dealing down at the kernel level on the OS. But there's something called an asynchronous OSD. So it turns out the OSD, there's a lot of overhead and inefficiencies in the OSD code itself. So which is to make it asynchronous and streamlined and remove a lot of the cruft. I don't know quite the right terminology, but a lot of inefficiencies in the OSD code. They're holding it back. Stepped up client optimizations. So we're seeing a lot of interest for Ceph deployments in, say, telco, for example, for NFV, in hyperconverged. And in hyperconverged configurations, and there we want to make some optimizations and see some opportunities in the client side. Now it's more important for HCI since they're all both together on the same system, so that we have a lot more ability to make some changes there. And then the persistent cache. So you might think caching, you want to make sure it's crash consistent. You don't want to lose data when the system crashes, things like that. And then of course, again, compression, encryption for BlueStore, so we can do encryption now, and compression. You don't get a lot of bang for your buck with compression BlueStore yet, right, but we're working on improving that. So of course that's with our QAT cards.
Awesome. Yeah. So I was going to inject a slide for SUSE that looked something like this, but right, my product marketing guy didn't really help me out.
These are really top. I mean, these are. Would you agree that? Dave, would you agree that these are pretty? I mean, these are some top. Yeah, items to work on to improve Ceph efficiency for things like flash.
Absolutely. So these are all absolutely key. And you look at the way that you can, the work that's been done where you can leverage flash technology, starting very early with things like cache sharing with SSDs, and then moving on. BlueStore is much more efficient than FileStore was. That was
we took all the cache sharing slides out. Remember?
Yeah.
That didn't work.
But it doesn't matter. I still put that in there. It's a good point to bring up. Things like the ISA-L library, I actually use this quite frequently when I'm doing erasure coding. The plugin that's there in Ceph offloads that from the CPU, so you don't need as much CPU horsepower for doing things like EC, which is great. So like I said, I was going to have a cool slide like that. I couldn't find it. Honestly, I probably have it somewhere in like the 300 presentations I have in my documents folder. I just ran out of time to search for it. I might need Hadoop on my laptop or something.
It would be very similar, because I mean, Intel works very closely with ISVs like SUSE and contributing to upstream code for Ceph.
Right. So the cool thing I was going to show is where we started with Ceph, which was when we released SUSE OpenStack Cloud. Very early on, we included Ceph with it as something that you could try out to see if it floated and worked for you. We turned it into a product about 6 years ago. And we've been continuing to march forward with very aggressively. You know, we've had CephFS in market for some time. We brought BlueStore to market first. We have an installation framework. And the most recent major thing we've done, in case you haven't been in any of the other Ceph presentations, is really around Ceph Dashboard, the management GUI that's out there for Ceph. It's started as OpenATtic on the SUSE side. It's technology where we acquired the people and the technologies from a company that was already doing it as an open source, brought them into the house. And then we took the concepts and the lessons learned to the community. And that's a really big thing, is improving the usability of Ceph. Day one for implementations, that's Deep Sea and Salt on our side. And day two operations, that's the Ceph dashboard. And that's a really key piece when we talk about enterprise consumption of something like this. So let's talk about the project. This has been my life for months and months and months. The goal is to really build an all-flash environment, identify a bunch of tuning options and the impact they have on CephFS. It says real-world scenarios for an all-flash environment. I have a couple of simulations for performance. I haven't actually included those numbers here. And the reason for it is, quite frankly, I'm not done with the work I want to do. So what you're going to see is you're going to see synthetic benchmarks looking at very specific workloads, you know, 4K random, 4K sequential, reads, writes separately, so you have some bearing on numbers as we walk through this. And the goal is to test on multiple devices. So we have some Optane P4800s, which Carl's going to talk about in a minute, some of these devices we have. So we have some P4800s, a bunch of SSDs. Intel helped out a lot with making sure we have the right hardware to do this work on. And we tested it in different scenarios where we have all SSDs with a RocksDB and wall offloaded the P4800. And this last one is still to be tested. Again, more work to do, always, but it's getting there. So there's a boatload of information. So the overall hardware environment, 10 OSD nodes. In each node, I have one Intel Gold 6142, 96 gigs of RAM, 12 SSDs, the S4500s, P4800 Optane, Mellanox ConnectX-4, 100 gigabit, dual port, goes up to, I don't have it on here, but I have 200 gig switches sitting on top of everything. 3 MONs, also co-located MDS manager services on those, 4110s, 32 gigs of RAM. And then the load gen nodes. So I have 2 that are the same configuration as these. And then I have 15 BL460 G6s, older servers, but they generate a lot.
96 terabytes?
Oh my gosh.
Typo.
I wish I had 96 terabytes, thank you. This is what happens when you're editing slides at 11 o'clock after wine. That's gigabytes. Thank you, Cedric. I owe you. Sweet, 96 terabytes. I want that.
Do you go bits or 100 megabits?
Yeah. So this is 100 gigabit.
Man, this is
legitimately.
Tough crowd.
Man, you guys are killing me. You're beating us black and blue.
Tough crowd.
All right, so the load gen nodes, these are older, but I've got a lot of them. And the blade chassis is connected in. It's got 160 gigabits of bandwidth into the backplane. So there's quite a bit of network connectivity where I can do a lot of load gen. So Intel, again, assisted with hardware, knowledge and tuning recommendations. So they've got a large body of work. A lot of this is in the public domain that you can see, where they talk about work they've done on very specific performance environments. And this is the most important one, a very open line of communication we've had with Intel. Carl and I have talked quite frequently. There's other folks with Intel that we talk to and get information from and have back and forth to discuss and understand the places that we can tweak, the places Intel really doesn't want us to try to tweak, even though we do it anyway, and things like that. But it's been very open and a very positive environment for this effort, and this effort should feed well into the general body of knowledge around Ceph, because this is a production configuration. We haven't turned off authentication, we haven't turned off logging, or anything that you would want to be able to make it supportable in an enterprise environment. So, with that, I want to let Carl talk.
Yeah, well, yeah, you know.
That's your advance right there, the middle one.
Okay.
Yep.
Up and down. So one of the things, kind of to the previous slide, one of the reasons that we were really excited to work with Dave is that, I don't know if you guys noticed at the beginning, but this is CephFS. And there is a ton of work that's been done on RBD, right? And Intel ourselves have done a ton of work with RBD optimizations on NVMe, and there's been some Rados gateway, but there's almost nothing on CephFS, really. And so we were really excited to work with Dave and fill in what we see as a gap, and something that we ourselves haven't really had time to work on. So we're really thankful and happy that Dave took that on. So I just really quickly just want to go over a couple of things. So I'm not going to give you a product pitch on Optane. Probably everyone in the room here has probably read about Optane, read about all of our, this isn't an Intel. What I want to do is focus in on why Optane and for Ceph and what makes it very useful. And this is a really important slide in the sense that Intel really basically has two SSD products. We have 3D NAND, which is just standard NAND. It's just three-dimensional. It's just a evolutionary progression of NAND. But then there's also something what we call 3D XPoint, which is Optane. Now the key is there's two keys. It's bit addressable, and there's no garbage collection. So this is why when we look at this most important on the right here is the latency. Because it's bit addressable, because there's no garbage collection, it does a couple things for us, which is very important for Ceph. Right? With Ceph, for high performance with Flash, we want consistent latencies. We don't want nonlinear latencies. We don't want a sine wave of latency. We want a nice flat latency curve. And because there's no garbage collection, because there's no write amplification, all the things that are both good and bad about SSDs are not present in Optane. So just on the left, we have a whole stack of building blocks that we have along with our SSD products. But here it's, again, high endurance. It's responsive under load. So when it's under high load, you can see that from our performance results and things, is even when you put it under pressure, high volume, lots of IOPS, high throughput, the latency curves consistently are flat. And it's a predictably fast service, so because of those flat latencies, there's no spikes. So we know that it's going to give us a consistent 5 nines long tail latencies. And then, of course, the IOPS are extremely high. But this is an important graph right here. When you think about it going from left to right, woo, I keep stepping on that. So hard drives, this is what we've been using for years, right? With Ceph, with all of our software-defined storage solutions. Notice drive latency is in blue, controller latencies are in orange, and the software is in green. So software latency is pretty fixed, right? That's the Linux driver stack for NVMe, for SCSI, for all your I/O drivers, your network. We'll look at the controller latencies, so your SATA controllers, SAS controllers. They introduce a fair amount of latency. We use SATA in this particular. This is one thing nice too from a real world perspective. We haven't quite crossed that inflection point to where everything's NVMe today, so there's still a lot of SATA chassis out there. But notice when we get over into our NVMe drives, all that controller latency goes away. And it's just the media. So the blue is the media. So that's just standard 3D NAND. This reflects that it's pretty standard. Even when we went to three-dimensional NAND, it didn't necessarily make it faster. It just gave us higher densities. But Optane on the right here, we removed all that drive latency and controller latency out of it. So it's a very low latency, which is exactly what we want for a caching device for WAL and DB and journals.
Did the software latency go up for Optane, or is that just an aberration?
This is resolution on the graph. But it's possible there's a little bit of additional latency from the NVMe. It's hard to say. I think that's just an artifact of the graph there. I mean, we could. And then, and just to reiterate, just notice the graph on the left here. It's kind of hard to tell, but what you see there, the curve to the up and to the right, under load, that's our standard P4600 NVMe drive, so 3D NAND. You can see it's pretty spiky latencies. It's doing garbage collection, right? It's doing write amplification. There's a lot of work that goes on inside of an SSD controller, basically, right? And it's reflected in that type of curve. But you notice that thick line on the bottom, that's the Optane latency. It's a flat curve. Running it all the way up, I can't quite see the number on there. Can you see that one on the left up there for throughput? You run it up to the left, and it just stays flat. Yeah. So again, under load, consistent latency, right? No spikes. In the middle here, disk writes per day, extremely high endurance, 60 versus 3. And you think about that, that's pretty important for your caching drives. Because what a lot of people kind of forget or neglect is the fact that if my wall DB drive or my journal drive fails, I lose all of the OSDs that are associated with it permanently. There's no recovery. So if I'm doing 24 drives in a chassis, two SSDs, so 12 to 1, if one of those fails because it burns out due to endurance, I just lost 12 OSDs. And those OSDs have to be rebuilt. It's not just that I rebooted, came back up, and Ceph re-equilibrates and figures it out. They're gone. So extreme high endurance is extremely important because those journal drives are very busy. Right? They're doing lots of random I/O. They're doing lots of reads and writes. Extremely busy. And then the thing here is efficiency. So we need smaller drives. So we can actually use a smaller Optane drive in relation to the total size of the cluster and the total size of the drive. So a little bit more efficient from just the amount of NAND you need, amount of drives you need for your caching. 60 DWPD, that's pretty good. That's extremely good. We were pretty happy with 3 for enterprise drives, but 60 is.
Yep.
And then
I don't understand that diagram on the right. So what are you saying there? You need less?
Yeah. So because of the efficiency of the Optane, because it's faster, you can use fewer of them. There's always a ratio, right? Of with hard drives and SSDs, it was always about 5 to 1.
5
was
to 1,
kind of
6
the
to 1,
classic
yeah.
ratio, right, of HDD to SSD. And then with SSDs, that ratio changes a little bit. But with Optane, you can have a higher ratio. So instead of say 6 to 1, 8 to 1, you can get away with say 12 to 1. So for example, in the configuration you have, which is a 22U by 24 drive, U.2 slots, we might put 20 SSDs, SATA SSDs, and 4 slots open for journals. We typically use all 4 of those. But with Optane, we can get away with 2 instead of 4. Does that make sense? So the total.
It seems like if you can fill it up faster, then all that happens is you fill the cache up faster and you can't offload it, right?
Well, but you're draining it faster. See, that's the key with Optane.
Yeah, it's not a capacity concern. It's more about how much I/O we can do against it at one time. So when we look at the RocksDB and Wall, some use cases use very little metadata in those. So if you know you're going to be employing one of those, you can actually size those way down.
Shrink them down.
And when you're in that kind of use case, it's all about how much I/O you can take. So there's 2 ways I run, and I always take the worst case between the two of how much RocksDB and Wall I need, and it has to do with throughputs and 4K performance on one, and then capacity on the other. On the throughput and 4K performance, it's fantastically higher on an Optane, just because the latencies are so low.
And it's a bucket and a drain, right? I mean, you want to drain the bucket faster than you fill the bucket, but you're not going to drain it as fast as you're going to fill it. So you need how much bigger does the bucket need to be to absorb that, before it overflows. With Optane, that drain at the bottom is much bigger. So not only can I bring it in faster, but I'm taking it out faster, which means I need a smaller bucket. I don't need to. Oftentimes we're over provisioning things, right? Just in case. But with Optane, you can be a lot more efficient about it. Much smaller bucket because it's draining out much faster. And this last one, this is what we did. So this is what it looks like, which would be, and we did put
different processor, but
well, Oh, I thought I changed that. Yeah. So it's funny when Intel does benchmarks. A lot of times you'll see another reason we like what Dave was doing, because he's using a real-world processor as well. So a customer's not going to put an 8180 in a SATA Ceph cluster. It's just right. It's overkill, way overkill for everything. So it's a 6142. But this is really what it looks like and what we're doing. So on the left is, I think you did this test exactly right. So you did a co-locate everything. And then what we did was moved over and, hey, let's put the Optane in here for our wall and DB, and then our SATA SSDs for data. And what that's showing, I believe you bear this out, is that just by putting this in here, we can increase the number of IOPS we're getting out of our cluster without having to provision more drives.
Yeah, certainly in some cases. There were a few that came the other way, but there may have been other things going on.
Use case dependent.
Yeah, and one of the key things I would definitely point out when we're talking about adding the Optane is I sat there and actually watched a lot of these benchmarks run for days. And one of the things that was very clear is while the benchmarks were running with the Optane in as the ROX Debian wall, the latency variance was much lower. It was a very flat line in what my latencies look like, which reflects back up a couple of slides, right? That's exactly what I saw out of Ceph, which was fantastic.
Well, that's always been a bit of an Achilles heel of Ceph, especially for supporting OLTP, right? Transactional.
Absolutely.
Is that nonlinear, right? That almost sine wave type behavior of latencies, because you're filling and draining and filling and draining. With Optane, it flattens that right out.
Yep. So are you guys ready for some more details? I want to dig in deep, and numbers are going to start showing up on the screen, and your eyes are going to glaze over, and everyone's going to die from boredom of looking at numbers. So just a real quick, I have cluster build scripts that I use to deploy the cluster, so I have a very consistent, fast way to build it. Basically, I run a command, it kicks the cluster out the door, I'm done. I don't have to sit there and fiddle with anything because it writes it all for me. Use FIO as the testing load generator. I use it in the client server mode. So I actually run it, the instructions are kicked off on the admin node of the cluster, and it sends it out to all the load generation nodes. And then the scripts for benchmarking, it's in my personal GitHub because I'm too embarrassed to put it on the SUSE GitHub right now because it's ugly and scary. But it is a automation framework around FIO. I've got a bunch of FIO job files that specify each workload I'm using. It goes out and actually handles all the automation, standing things up, running the test, collecting the benchmarks, putting it into JSON outputs, getting it ready so I can ingest it into another system and use it. So the configuration, base OS, Celeste 12 SP3. This is SUSE Enterprise Storage 5.5, which is upstream Ceph that we've hardened. It is Ceph Luminous. I started off with the Mellanox inbox driver. There came a point in time during the testing that I became convinced that the driver was a bottleneck. And I shifted, did some step back, did some iPerf testing, and then made a shift to the Mellanox driver, straight from them. Hey, don't harass me yet.
Right?
Yes, actually I did.
So we fixed it then.
I don't know, I haven't looked. Sorry, I've been busy. So I shifted to the Mellanox driver and performance went up over the NICs, which was important. And everything in the system is set for a performance bias. It's set for performance node. There is 0 power savings happening anywhere in this system. And that includes doing some CPU tuning I did later as well. So,
Who cares?
what was that? Sorry.
About now down.
I will actually talk about that very specifically in just a moment. You'll see.
What protocol were you running over the Mellanox?
IP, TCP IP. Yeah. Ceph does not support RDMA today, at least not in any kind of fashion you want to use. I'll just leave it at that for the moment. So it's an iterative process. The total number of test steps I have gone through would be over 30 iterations right now, with each test taking about a day to run, plus little micro benchmarks in between as I'm making adjustments. I started with a couple of baselines, and I'll talk about those when we get to them. At one point, I shifted down from 3 replicas down to 1 replica to watch for very specific changes in the behavior of the Ceph OSD code in relation to the IOP improvement and latencies. Along the way, I sent lots of emails, didn't I, Carl?
Yes, you did.
There was a lot of communication back and forth talking about some of the things I was seeing. Take fresh measurements after every tuning for everything I did. Shifted to 17 clients. Along the way, I'll kind of reflect some of these points in the numbers. Hiccups. So I encountered a situation where FIO was losing test results. That actually affected the first couple of runs. So I did note what we had to do to fix it. Basically, it's no updates going out while it's running. It just collates everything at the end. And in one step, when I was adjusting kernel stuff, I inadvertently dropped a multi-queue block I/O for a few runs. I added that back, and stuff like this happens, right? I did find updates I had to make to my benchmark scripts here and there because I actually wrote in functionality to take advantage of Ceph device classes for my scripts. And that always creates bugs when I write code because I am not a software engineer. So numbers. These are latency restricted. So I use FIO with this crazy thing that says basically almost every I/O has to be under 10 milliseconds in any given 5-second window. Okay? And I do this because I really want to know if we have to hit this performance number, if we have to hit a 10 millisecond max latency, where are we going to be?
Bandwidth is measured in what?
Yeah, I'm getting there. So bandwidth is in megabytes per second, megabytes, however the heck you say it.
Megabytes?
Yes. Ceph does not excel at what? 4K I/O. All right. If you think it does at low latencies, remember we have this 10 millisecond window, and I'll show you some changes on that in a minute. It doesn't perform great. But hey, it's there. It can do a job. But if you're trying to run OLTP, don't. Hannes has many other better solutions we can talk about. So this was the first baseline. I also put the 4K here. I've got 64K numbers, 1 meg numbers, 1 meg, 4 meg, 64K numbers, all as well, across RBD, CephFS, erasure code, and replication. I'm not going to try to put it all on the screen because the spreadsheet has over 1,000 lines in it. So it's a little brutal. So initial tuning. First step after the baseline. Let's turn off some Spectre and Meltdown stuff, right? Because if you've been reading anything, you know that Spectre and Meltdown hurt anything that goes from kernel to user space and back many times, and Ceph tends to do that. Enable block MQ. So here's what my kernel command line looked like. It reflected what was in our TID at the time. This would have been late January, I think. I will say there are some additional Spectre v4 or whatever it is, Spectre v4 plus L1TF stuff that we talk about in the later step. Here's the TID. So what's performance look like? Well, CephFS 4K random reads went up. Not surprised there. 4K sequential writes go up. And the average latencies didn't change appreciably. Okay.
How come that the raw access has a slower bandwidth than, or lower bandwidth than the file system access?
Do I look like a CephFS developer? Really?
Buffering.
I don't know. Honestly, where's Jan? Where's Jan when I need him, right? Yeah. Anyway, so we do have guys here that can discuss some of this. I suspect we're seeing there is some caching that happens in CephFS, and I think that's some of what we're seeing.
Buffering.
Yeah, it has some buffering that does go on. But the numbers did improve.
What is the size of the files?
So the files are, I have to think about this because it actually calculates based on total capacity. So I had about 120 terabytes of SSD, so it would have been, this was across 2 nodes. The files would have been about 100 gig files that it was working with.
So you're right, it took more than one OSD effect.
Yes, yeah. So this is 16 jobs queued up, 32 per node, 2 nodes doing it in this case. Okay, so this is all 2 node until we get to about step 10, roughly. The 2 nodes with 100 gig E and stuff doing the load generation. So I dropped the latency targets for file because I got really interested. How far will we go? And what happens to my average latencies? So I dropped the average, dropped that off, and you see suddenly, without latency caps, we get not bad bandwidth. Still not great considering I've got 120 SSDs, but hey, it's a little more interesting at that point. The average latency, not bad. Max latencies, well, you get the distribution's a little further out to the right, so it grew quite a bit. See how I'm doing on time. I just got 30 minutes, I'm good. The mixed workload was interesting. You see the read bandwidth jump. Start looking at 4K random read only. We're over a gigabyte a second. Not too shabby. I'm okay. I'm getting okay with this. Again, the average latency, not bad. So I kind of point out some highlights down here, but the net is it's not too bad. The curves are very flat, and this is with the P4800 as the RocksDB and wall offload. So we did some stuff. I looked at it, got down a few more steps. Things weren't changing. So we did the NIC driver we talked about and picked up a pretty significant average increase going across it. Still not pushing a full 100 gig. It's 100 gig driver and 100 gig switches and NICs. So there's more tuning to be done there. I just ran out of time to mess with it. So there's more to be done.
I did similar testing with PowerShell.
You see similar? Do you see similar type stuff?
So no, and what I've seen is that we pretty much max out the system after 40 gigs per second. Because that actually, 40 gigs per second requires you to have at least 32 CPUs. If you don't, you never reach it.
So I'm feeling pretty good about myself right now.
That's actually quite impressive.
Yeah.
I'd be very much surprised if you get more than that, because simply the CPUs are maxed out. You can't push more.
Well, the CPUs still had quite a bit of headroom in them in these systems. So, well, we can talk about this because
it's not necessarily the CPUs, it's the combination
right.
of CPU, PCI, both.
Right. And that's where I was going to go, see if. Yeah. So, and that would make sense, right? So, not doing too bad. Here's the NIC tuning we did. You guys can have all these slides afterwards. There's a bunch of things we touched. Obviously, oh, hang on, jump too far.
Go back. Yeah.
Jumbo frames, I flipped on. Adjust ring buffers, adjust the buffer size on the NICs, adjust RSS across the NICs, do a little bit of TCP tuning, blah, 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 blah. If you know what all this stuff does, great. And then ran the Mellanox tune on top of that to see if it came up with anything else. So this took a long time. Yeah, so these are, the load generators are in a mode 6 bond. The OSD nodes are all in LACP. We'll talk later.
Why?
No, because I tried it without. So after network tuning, where do we go? Not a whole lot of difference in the grand scheme of things. You know, slight increases. Went back, started watching things. I ran this benchmark like 8 times, looking at different things, and then it occurred to me, oh yeah, you know what I haven't done is I haven't looked at what's happening on my load gens. And yeah, we just couldn't drive enough throughput out of the 2. So what do we do next? We go to 17. So we go to 17, suddenly my 4K random read, ka-chow, I'm at 4 gigabytes a second coming out of a Ceph FS file system. Look at those numbers right there, 10654,64590. So 1 million random read 4K IOPS out of a Ceph FS cluster. That's pretty cool. With an average latency of 7.83. We are not a pure storage EMC NetApp, but I'm pretty happy with that number. How do you feel about that, Carl?
7.8 is within the range of a POSIX block storage.
Yeah, so
7.8.
Feels pretty good. The write performance.
It'd be nice to get a little lower, but 7.8's.
Yeah.
You're not going to get timeouts or anything.
No, we're not going to be like crazy fast. But I'm pretty happy with that number. CephFS random writes 422. I find it interesting that writes and reads do something interesting later. We'll talk more about that as we get down there. So, overall, the numbers are pretty darn good at this point.
So the max latency, that's actually 11 seconds?
Yes. So one of the problems.
Too high.
Yeah. One of the problems you have is, quite honestly, with Ceph, you still have the ability of long tails to hang out there. Right? There's a lot of work that can be done on the OSD code itself. The messenger, there's a bunch of places for optimizations. Yeah, the async stuff that Carl was talking about. Those are things that will come in. There's some upstream work was talked about in the devel list the other day about URing, using that significant drop in latencies and better management. So things that make sense, right? So this is all good information. So let's change up the config. Let's drop the RocksDB and wall off the P4800 SSD only config. These numbers got better as far as the maximums. The max latencies, some of them are a little better, some are a little worse. But what they did do is they got extremely erratic in the way that the latencies happen. You'll see it, the system would go, you'd be carrying high latencies for a little bit, and then suddenly it drops as, it looks like a garbage collection or something running in the background. Just interesting things. But the numbers are pretty good. Again, 120 SSDs. Could do a little more than this, do a lot more than this if you were doing it all local, but not too shabby. So I thought I'd throw in some other numbers, 64K performance, right? So 64K mixed, 2 gigabytes a second, just shy of 500 on the right side. You go to a unidirectional I/O, going CephFS 64K, 7 gigabytes a second and 64K IOs, not shabby at all.
Oh, can I switch that back to the 4K? Oh, you explain the curious.
The bump? Yeah. So what is the barrier? Does anyone know what the barrier is where things deal with RocksDB and wall on Ceph? It's below 64K. So once we pass 64K, it's going straight to disk. And that means we're leveraging what the SSDs handle well in writes. And what's the average size it's going to write in? It's taking a write into the SSD. It's a 4K write on the back end, right? But it doesn't like to coalesce around 64?
Yeah.
So we're actually hitting a really sweet spot on these SATA SSDs. These numbers are not bad.
Your read bandwidth went up right now.
Yeah, so that I think has to do with the fact that we're now dealing with a lot more I/O coming off of the SSDs for the metadata that's occurring, right? So those small metadata operations are happening off the SSDs as well. 1 meg performance, 12 gigabytes a second on sequential writes, 4 on the reads. All right, so I have one P4800 PCIe board in every system, and I thought, you know what? By golly, we're going to build a cluster out of that, and we're going to see what it can do, because I'm a geek and my propeller's twirling a little bit. So here we go. 4K mixed. These are uncapped IOs. 342, 87,000 write ops. 1.5 gigabytes a second. Average latency was a little higher. They can take a lot heavier beating than the SSDs can before the IOs just start falling out of the air.
Can you clarify what your hardware configuration is here?
Yeah. One P4800 Optane board
right.
is the storage device. It's one OSD per server. Okay. You got it. One OSD per server, 10 servers, 100 gigi. Yeah.
How big are those Optanes in there?
These are the 7, whatever it is.
If you run this test again, you should try putting a couple OSDs on there.
Yeah, I didn't feel like messing with that. This was done at like midnight one night. I've been working crazy hours. So I thought I'd give you a comparative slide with some data extrapolation on the end. IOPS per device. So when we have it in the offload mode, and this is looking across 4Ks on the various write patterns, you notice the massive IOPS per device we get out of the Optane boards. You would expect some of that being an NVMe device, This number's pretty high. I need some like some P4600 or 3700s in the systems to test to see how it compares. I don't know that there'll be that big of a jump because, quite frankly, the bottleneck is in the Ceph code at this point.
Yeah.
The cards will do much more than that.
200 megs per.
Yeah, they'll do a million.
Yeah, the cards will do much more than that. Yeah.
They'll
Pretty
do
much.
A million IOPS
You're exactly right, Hannes.
per device.
But it's an interesting statistic, and especially when you start looking at things like this. You know, we're 8x here. This is, you know, just massive differences we're seeing in performance. So, very intriguing statistics. So what about 2x replicas? Well, if you absolutely don't care that you're going to have an upset stomach thinking about data loss in a large Ceph cluster, you could do a 2x. I don't recommend it for anything that you really care about. If losing the data will get you fired, do yourself a favor and don't do a 2x replica. But if you're going to do it,
But Blue Store is doing checksums.
Blue Store's doing checksums, but it's the risk of device
more.
failure, node plus 1, right?
Yeah.
So you lose a node plus 1 drive and a 2x, your data's gone. So 3x is what we recommend, or erasure code, and I'll actually talk erasure code in a minute. So I thought I'd show you 3x versus 2x, pink and purple. Pink is the 3x, purple is 2x. As you would expect, not much difference really on the read side, right? Because it's reading from the primary PG back. But on the write side, we saw some reasonable improvements on some of these write patterns. And it has everything to do with the OSD code. Remember async OSD? Yeah, that would be a great thing. So.
Why do you think there is any difference in the read? Does the same thing? So what's the primary?
Yeah, so it's the same thing. I'm not sure. You know, in every test there's variation that happens. Some of it might be the random pattern because I don't have it running a set random pattern. So it could be that one pattern has slightly more randomness than the other, and it's creating some variance. But you know, you're within a few percentage points tops. So I calculate, you know, just call that out as noise in the grand scheme of things. The one thing that kind of showed up a little is the read average latencies came down. I'm not sure why that is. So that's something. These numbers, to give you an idea, these numbers are hot off the press. I actually put this chart in last night at 1 a.m. So this stuff is still live and happening. All right, so we're going to flip out of the presentation deck for a minute. Come on, die. Thank you. Where's my results sheet? Pull this over for you guys. All right. Now this is a bit of an eye chart. This is where I'm recording all my results. It's crazy. So up here I have some erasure code numbers. Let's see what tests I have. This is step 20. Okay. Just so I can make sure I know what I'm talking about. Step 20 is P4800, so that's erasure code. And then, so we should care about step 19 and step 20. And a test that I was actively running, which is probably not there. Okay, so with erasure coding, 4K, and you might not be able to read this very far back, 4K mixed, 59 megabytes a second. Again, this is P4800s. This should be really high numbers. The code is where you're dying on it. Erasure codes are rough. Latencies were a bit high. Read was not great. You move up to 64K, you start getting the 64K stuff. Things get a little more interesting. Still not fantastic, but it's there. Go up to large blocks, 5 gigabytes a second, 2 gigabytes a second, that kind of number. When we go down to what I say the all pink was that the 2x? SSD only. Okay. So in the SSD only, there's a lot more devices, and that actually plays heavily into the erasure code being more efficient. So and this is all replicated, so you've seen these numbers. Do I have, what's this one? Step 21. So this is 2x. Did I do? Yeah. All right. So in 2x replica, or 2x case, I ran this with the ISA plugin enabled. So we'll look at a 4K mixed. Let's scroll over. That is line 20. Line 20. Let's get over here. All right, there's line 20, 206. So it's not a substantial increase here. And then 825. So it made a little bit of a difference, not substantial in this case. The bottleneck is really in the code. Okay, it's in the OSD code still. There's, like I say, a ton of inefficiencies. To me, the most interesting data point we've hit is the fact that we can drive 1 million IOPS. We can do it actually relatively early in the tuning that we've done. The tuning after that becomes mostly superficial. I've done things like increase the number of threads that BlueStore uses. There's still a lot more options to tune. I don't know if you've ever looked at the BlueStore options. There are tons of them to do. I also want to try it with doing compression on and off, see how that affects things. Probably more on the all SSD or spinner side. I do have a large spinner cluster as well, but not here. So interesting results at this point, I think. So, Jeff.
What erasure code strength do you use?
So this is with a 3 and 2, I think.
3.2?
Yeah, I think this is a 3 and 2 is what I have set up right now. So not a great data protection scheme, but it fits within the size of a relatively small cluster. So other questions before I go to my wrap-up slides, since we're almost done?
When do we expect the code modification for the OSDs?
So the code along the OSDs, there's constant updates, right?
Yeah.
So there's some improvements in the Nautilus code base, which is SUSE6. So I'm very much looking forward to getting the SUSE6 beta loaded on this cluster and doing some of the same benchmarks again and see where we come out. It also takes, SUSE6 also uses SLUS 15 SP1. In SLUS 15 SP1, we have new I/O schedulers, thank you, Hannes. Things that should help improve the way I/O is handled throughout the system for getting to disk. And then stuff like the async OSDs.
That's a 2019 project. I mean,
Yeah.
It's
Meaning
non-trivial.
upstream, it's
I mean, it's non-trivial, and it's a 2019 project.
work in progress kind of thing,
yeah.
right?
It's almost a complete rewrite.
Okay, but it will be delivered this year?
That I can't.
Okay.
Yeah.
It will be worked on this year.
I can't,
How's
can't
that?
commit one way or another. I mean, we're contributing, but we're not the only people, so we don't control when it gets ultimately released. But it is a non-trivial exercise to do that.
Were your OSD single socket or dual socket?
Single.
Single.
Yep.
Yeah.
I hate QPI. Sorry. It's me. All right, so thoughts on architecting clusters going forward. QLC drives hitting the market. We're continuing to see that price drop. At some point in the future, we will see a crossover, right, between density on those devices and spinning media, where we can get a higher density SSD for the same cost per gig that we see out of spinning. That's not going to be today, probably not this year, maybe next year, 2 years from now, 3 years from now, but it's coming. And the number of cluster architecture requests we get for all flash clusters is going up dramatically. We see a lot more of this coming out of the field.
Just to pile onto that.
Yep.
The crossover to 7,200 RPM drives is going to take a couple of years.
Yeah.
Absolutely.
The crossover for 15K and 10K drives is happening imminently.
Absolutely.
No,
It's already done.
It's happened already. Western Digital just announced that they stopped development on their U.2 2.5s, right? So Seagate won't be far behind. Yeah.
Seagate still ships them, but it's not.
Yeah, no, but they're the
Yeah, 15K has been dead for a while. 10K this year, last year. I mean, they're done. I mean, the largest you can get is a 2.7 something terabyte drive, and they're not making them any bigger.
And 7.768s are easily available.
Significant volume still of 10K drives.
Yeah.
Wouldn't want to debate it,
But the
Yeah.
Used with Ceph, I don't know.
if there's a
Yeah, not with Ceph. We just simply don't see it, right?
Peace.
Yeah.
So when we're talking about what's happening in servers, U.2 format for NVMe. You guys know about that? It's a PCIe bus.
Standard.
I hope everybody has seen this and understands the greatness that that is bringing to our servers. I love it. Come on. So it does make a sense to have a cluster where you have a mix of slots, right? So you can architect a cluster with spinners, SSDs, and NVMe all in front slots in the server. And you can create pools using the device classes in Ceph. So you can have one that's very high performance, or you can use use Optanes in some kind of form factor that makes sense here, where you offload RuxDB and WAL to it, and then you have maybe an all SSD pool that has no offload. That's a completely legit configuration. And then there's this great thing called CAS, which I don't have on this slide, it's on the next one. Intel's cache acceleration software that you can actually use to accelerate the spinning media. So you can use it in write back, write through, write around. Yeah, I think that's all of them. And you can tune it based on the I/O that's coming in.
So not that I want to do a product picture or anything, but on your second point, our 45As have got 6 NVMe's and 45 HDDs. So exactly what you're doing, you can do the high capacity archive type one, and then the
Absolutely.
Yeah.
So exactly to your point. So I'm sure other vendors are doing the same.
Well, I'll just reinforce that one. Yeah.
Well, we use device classes as well, so it's really nice.
Yeah.
You can have a device class for the NVMe's and one for the HDDs.
I'll reinforce that statement there in that we've seen using, so a simple upgrade to an HDD-based system, especially something like yours, which has the slots in it, would be to drop a couple Optanes in there for journaling or WALDB.
Yep.
You don't have to swap out and move to SSDs. Just dropping that in there can not dramatically, but significantly increase your performance and stabilize your latencies. So it's a nice quick upgrade. Yeah. You just have to repave the server because you got the journals, but that's doable, right? But it's
there are NUMA nodes, so there's more complexity than your point.
Absolutely. We've already beat this last one to death. Ceph is a work in progress. It just keeps getting better, which is great.
Yeah.
A couple years ago, we would never have hit 1 million IOPS in this config because the stuff is there. So the future goal, I want to do some more testing. Shocker, because it's playing in a lab with really cool hardware. I want to do one with ICAS, both sticking it in front of SSDs, one in front of RBD. What?
Bcache?
So Bcache is on the list, as is LVM cache with 6. So because that's part of what we've got. Yeah, I have to test them both. Talk to Lars. I need to test them both. So I want to capture very specific benchmark information as it relates to workloads like rendering. So I already have one that simulates virtual machines to some extent. I've got the starts of one for a rendering workload. Think media and entertainment industries. This could actually start getting interesting as we get faster and faster. There are some very specific read and write mixes, I/O size mixes that make sense there. So,
and they're all stuck with POSIX requirements.
Yep.
So they can't move to object storage, and they don't want to use block.
Yep. So I actually posted a message out to the FIO devel list the other day about doing multiple ranges inside of a single FIO job, where you have a distribution, and Jens responded back with something about using shares, and someone needs to develop it. So if there's a developer in the room that wants to work on FIO, talk to me. I've got a project for you. And then obviously repeat the testing on SUSE, because I think there's a lot of interesting things that are going to happen with SUSE, both because of the underlying Linux and with the Ceph code itself. Some great improvements there. The good news is we're in the world where we can build a reasonable, from a price point perspective, not great, but a reasonable 1 million IOPS Ceph cluster. I want to see more of the metrics get into the million IOPS, not just very specific read patterns, but we're getting there. I hope to see a few more things cross that barrier with SUSE 6, and down the road with SUSE 7, which will be a year after SUSE 6 comes out. Good news is it's getting there. Intel's working there. We're working there. There's a lot of work under the covers on I/O paths inside the Linux kernel. That's guys like Hannes' team work on stuff like that. So keep watching it. Know that we can now address some higher performance use cases. Start thinking Some HPC use cases fall nicely into this. Things a little better than just shoving data out there that's going to sit cold. We've got enough performance, we can do something with it now. So that's kind of where we're at. Thank you.